Hello again, Mr. AST here. Today we're going to continue our discussion on energy. This is specifically from 11.1 still. So the first thing we're going to talk about is energy transfer. We've kind of alluded to this previously that basically we know that if we hold an object suspended above the ground, once we release that object, it's going to pick up speed. So what's happening there is we're transferring gravitational potential energy into kinetic energy. And most of the time, we're going to be considering energy transfers. So another example of energy transfers are friction. When you use energy to move something and the surfaces rub against each other, the friction generates heat, which is thermal energy. And thus we have some of our kinetic energy being transferred into thermal energy. And we transfer all sorts of energy. Most commonly, we transfer electrical energy, for instance, into radiant energy to make light, or into kinetic energy to make motion, and so on. So we're going to work through a quick example here. A 4.25 kilogram ball is brought to the top of a 10-meter roof. You drop the ball off the roof from a height, spelling errors of course, off the roof from a height of 1.12 meters from the roof. So let's make sure we got an idea what's going on here. So we have a roof. If we call our ground 0, that's our reference level. The top of the roof is 10 meters. And when we throw the ball out, we're an additional 1.12 meters above that. So that means the total height of the ball is 11.12 meters. So part A. What is the ball Earth system's gravitational potential energy relative to the ground? So if the ball is being released from this height here, then we have to use our total height of 11.12 meters. Now, appropriately, we should round this to 11.1 if that was our final answer using sig figs, but that's not our final answer. What we have here is we have actually part of our process. So formula for GPE again is mass times gravity times height. And in this case, that's 4.25 times 9.8 times 11.12 in this case. And we will get 463.148, but with 2 sig figs limitation, that would be 460 joules. So the gravitational potential energy of the object is at 460 joules. Part B. How much work is done lifting the ball to this height? Well, if we assume, now of course we could argue if you walked up a bunch of stairs or something like that, but let's think about just the vertical motion here. If we started at 0, a height of 0, that means our gravitational potential energy in that reference frame was 0. Because if h is 0, everything's 0. So we went from 0 to 460 joules. That's our change in energy. Remember, work is equal to the change in energy. So in this case, it's just 460 joules of work was done to get the ball to that height. All right. Part C. If we drop the ball, how much kinetic energy does it have at a height of 8.50 meters? Now, we're going to ignore air resistance, friction, and a few other things here. We could do this in a rather complicated way. The complicated way was to go, well, 8.50 meters, we can kind of work backwards using what we know about gravity and kinematics to figure out exactly how fast it's going and then establish its kinetic energy based on its velocity. But if we understand the key concept here, the energy transfers, so let's find its gravitational potential energy at 8.50 meters. So the GPE at that point is the mass has not changed. Gravitational constant is still 9.8. But now we're at a different height. We're at the height of 8.50 meters. And we do our math there, and we get about 354.025. So I'll call it 350 for now. We're going to need to not use that though. Remember, we have rounded versions here. We're going to use the non-rounded in a second. So 350 joules at that point. So if we look at it, we lost about 110 joules. So all the gravitational potential energy we lost, it was turned into kinetic energy. Now, of course, some of it was turned into heat as the air particles collided with the object, but it's a very small amount for our frame of reference for what we're talking about. So I'm just going to go back and I'm going to subtract the original versions of these two numbers to avoid sig fig loss, and we will get, restricting ourselves to 2 sig figs, we get 110 joules. So what I just did was subtract the original versions and rounded it appropriately, and I actually got 109.123. So it would have 110 joules of kinetic energy because any of the gravitational potential that was lost had to be transformed into something. In this case, it's kinetic energy. All right, part D. How fast is the ball going when it hits the ground? Well, when it hits the ground, we know it's going to have 0 gravitational potential. So that means all of the original gravitational potential pretty much has been transferred into kinetic. So we can use our formula that kinetic energy is equal to 1/2 mv squared. And we know the kinetic energy is 460. And again, how do we know that? If when it hits the ground, when this object finally hits the ground, its gravitational potential energy is going to be 0, which means all of that gravitational potential energy we started with is now kinetic energy. So 1/2, the mass is 4.25 v squared. So if we solve for v, we would get v equals the square root of 460. I'm going to use the unrounded version of that, however, the 463.148 as to not lose accuracy, divided by 1/2 times 4.25. And I get, now I have to restrict myself to 2 sig figs here because in this process I used 9.8, which is limiting our calculations. So I get 15 meters per second. So we can use what we know about these two formulas and how they work together to use one to solve for the other in circumstances. All right, let's move on and talk about some other types of energy. So elastic potential energy, we're familiar with the word elastic as in something that is stretchy or springy. And that's kind of the right idea there. Now, elastic potential energy, potential means that it's stored. So the formal definition is energy stored in an object's change of shape. So let's go over a couple quick examples that we're familiar with. So number one, rubber bands. If you stretch a rubber band around 2 posts, you can then stretch it backwards and store energy. Then you use that energy to like shoot something or snap your friend or whatever you do with rubber bands, right? But that's the idea of the stored energy in a rubber band. Another one that is sometimes used is natural substances like bamboo are very flexible. So if you have a piece of bamboo, you can actually bend it, and that will store potential energy that can then be released into kinetic energy. So almost always the concept is you store the potential energy to release as kinetic. Another example is spring. You could compress a spring and then make sure it stays compressed so that once it's released, once the lid is blown off the top of that, it shoots out. And that's an example of stored elastic potential energy. So we don't really have a formula for elastic potential energy, but we can kind of work backwards using what we know about energy transfers to find how much elastic potential energy was stored. Now this is not a perfect example, and we'll talk about that. If an arrow is fired from a bow and its initial velocity is 70.0 meters per second, if the arrow weighs about 21 grams, so let's convert that real quick. We don't like grams. We're going to go 0.021 kilograms. What is the elastic potential energy that was stored in the bow when it was drawn tight? So we draw a bow tight, it then releases it, and we transfer all that elastic potential into kinetic. Now, we're going to work this problem out as it's assumed, but there's some flaws in the reasoning here, and I'm not sure how much they'd affect it. So number one, when you have a bow, it's not just the arrow that is the weight, you're also moving the string, which has weight. And I think that might actually matter here because the arrows are very light and the string is very light, so it's not like one is way lighter than the other and thus shouldn't be considered at all. So what we're doing here is we're actually working backwards. We're going to find its kinetic energy at the start and then say, well, all that kinetic energy came from the stored elastic potential and work back there. So we just do our 1/2 mv squared. In this case, that's going to be 1/2 times 0.021 times 70.0 squared. And when you do that calculation, you get 51.45 joules. So theoretically, that was our elastic potential energy initially. So let's see, we have 3 sig figs here, so it'd be 51 using the 5's rule. Remember the 5's rule, 0.4 joules. So again, that's not perfect, but that could be a good estimate about how much elastic potential energy was stored. All right, let's talk about two final types of energy. So before we get into these, I want to talk about, these aren't the only types of energy we're going to avoid. Like there's chemical energy, there's radiant energy from light, and we'll talk about some of those things as we get into topics specifically dealing with them. So first thing we're going to talk about is mass arrest energy. This isn't formally defined in the book, but it basically, Albert Einstein determined that based on the amount of mass something has, it has inherent energy. And so we're going to define this by Einstein's formula here. Rest energy is called E sub 0, and it's equal to mc squared. And we've all heard this before, E equals mc squared. So let's discuss it briefly. What he determined was that everything that has mass has inherent energy. But usually, unless we're dealing with stuff like nuclear reactions or particle physics situations, the amount of energy and mass relationship isn't really on the scale of what we're talking about. So when we talk about nuclear reactions and particle physics, we're working in scales where this actually matters and it comes up. But if we are working on a day-to-day scale, dropping things off of buildings, firing a rubber band, this is not going to play a factor in how we consider those numbers. So let's just give a real quick scenario. Let's say we have 1 kilogram of material. Let's just say it's perfect, 1.00. Well, c is the speed of light, and the speed of light is 3.00 times 10 to the 8th meters per second, roughly. So we have this situation where the rest energy of just 1 kilogram, remember that's about 2.2 pounds, is times 10 to the 8th, and then we have to square that. That's going to come out to be 9.00 times 10 to the 16th joules. So that's a massive amount of energy. That means that every small piece of matter has a massive amount amount of energy, and that's called its mass energy or its rest energy. And that was kind of a crucial part to Einstein's theory of relativity and the relationship between mass and energy. All right, last one we're going to talk about is thermal energy, because it's something we deal with in a very common sense. A lot of times when we deal with energy, what we call energy loss, it's because we're losing energy to thermal energy. So thermal energy is the sum of the potential and kinetic energy of particles. So basically we perceive this as temperature. Temperature is a measure of the thermal energy in an object. And the reason why it comes up is if we think about the particles, let's go back over our friction example. So if we push something, we know from our studies of force that friction will provide an opposite force, right? But if we think about what that means, we start off with some kinetic energy. Let's say we push that at 1/2 mv squared. Well, we know that eventually, no matter the mass, no matter the velocity, in our environment, that's going to go down to 0 because friction's going to stop it. So that means it has 0 kinetic energy. What happened to that energy? Well, it didn't move levels, so it didn't go up or down, so it can't be gravitational potential energy. It has to transfer to some other type of energy. We know friction exists. We know from experience that friction makes things hot. If you've ever touched the end of a drill bit that's been boring through wood, you know that's hot from the friction. If you rub your hands together, you know that's hot from the friction. So whatever energy we impart upon that object, as it moves and slows down, right, it will transfer into friction, which will be heat. Now, how is that true? Well, think about this at a smaller scale. Let's zoom in to what's going on there. What's going on there is we have two surfaces in contact, and those two surfaces have particles in them. And as they rub against each other, it bounces their particles around. Particle motion is part of what thermal energy is. We perceive particle motion as temperature. And so this is a very important concept. It goes back to like why machines aren't 100% efficient and why friction generates heat and how this pertains to the concepts of energy. All right, guys, that's it for this section. Next time we'll be doing a lab, and then we'll be talking about some more concepts with energy. See you then.